Morning, everyone. So yesterday we started looking at acid dissociation constants, Ka and Kb values in a little bit more detail. Pretty much, if this acid dissociation constant is high, it means the chemical is a very good acid. Even though overall it is still in the weak section, it's still going to be in equilibrium. It has an equilibrium that's a little bit more to the right-hand side than any acids lower than it. We found a nice expression between K and Kb. Let me just give you a quick practice of that. And then today we're going to look into actually calculating the pH and the pOH of a solution. Right. So just as a warm-up here, I want you to write the expression for HS minus acting as a base and calculate the value for Kb. So calculate the base ionization constant because this one here is acting as a base. And then just to make sure we're okay with dealing with Kw kind of concepts here, we'll do more of this practice question in today's lesson. I want you to calculate the H3O plus. Remember, H3O plus is just the characteristic acid particle. Calculate the H3O plus and the hydroxide for 16 molar nitric acid. Okay, so I'd encourage you just to pause the video, try it out for yourself. Assuming that you've done that here, let's start off with HS minus. They're specifying, although this one here is amphiprotic, it could donate its other H. It could also pick up the H again and reform H2S. We want HS minus acting as a base. So on your table, it's going to be written HS minus, while as a bronze tellurium base, it's supposed to just absorb a proton. Absorbing a proton, it is in that weak section, so therefore it's going to be in equilibrium. That's all it says, writing right to left. Remember, your table unfortunately has things that are simplified. It is the correct equation. By losing H+, we are going to overall have a net excess of hydroxide. Remember, before we write the equilibrium constant or even try to calculate its value, we need to write out the complex equation. On the base side, for the complex equation, it's like adding hydroxide to both sides, right? Algebra says whatever you do to one side, you do to the other side, it's fine. And therefore, my complex equation is actually HS minus, H plus and OH minus forms water. Basically, the HS minus is going to steal the proton from water. They're going to then create H2S, and what's going to be left behind because of the water is because it's the base particle that I leave. The constant for here, that's when I can define Kb. It is the constant for the base. It's going to be products over reactants, H2S times hydroxide all over HS minus. So that is the expression so far. If you remember on the table here, I'm just going to give you a quick gist of it. We have our acids, we have our bases. We remember yesterday we derived the expression. The Kb is equal to Kw over Ka, but I wanted to emphasize here, it's the Ka of the conjugate acid. It's the Ka of the partner. So let me just show you the two reactions that we're interested in for this question here. If I look up H2S, H2S is fairly far down the table. H2S, there's an equilibrium, H plus and S minus 2 here. Oh, sorry, HS minus. That one there has a Ka value. On my table, they just give you Ka constants. The Ka constants is 9.1 times 10 to the negative 8. All right? So that is a Ka. That is telling me how good my H2S is in coming forwards. Right? We also have HS, because it was amphiprotic. HS minus is a little bit farther down the table. I actually realize, again, our acid-base table here isn't an exhaustive list. It doesn't contain all the acids that we might care about here. H2S is already so far down the table, we actually don't get to see the HS minus's Ka value. But no problem for us here. If you want to find the Kb value of HS, we want to look for it on the base side. We want to see which reaction is actually going in reverse. So when I try to do a Kw over Ka, we know Kw, that is a constant at 25 degrees. 1.0 times 10 to the negative 14, we're actually going to divide by the Ka. This Ka was for H2S and coming forwards. That's exactly the Ka I want to divide for me to figure out how good my reaction is going in reverse. So 1e negative 14 divided by 9.1e negative 8 gives me here a Kb value of 1.1 times 10 to the negative 7. So although, reminder, on your table, you're not actually given the Kb values, we can always just calculate it from the Ka from my partner. And as a general rule here, if I am really far up on this left-hand side here, I have a relatively stronger acid. Because H2S is fairly far down the table, by the time we get to H2S, this constant is very small. The HS minus as a base is actually getting stronger. It's actually stronger as a base the lower it is on the right-hand side. Right? So just look out for that there. In our next chapter on redox, we're going to have another table. It's set up pretty similar. The strongest is going to be on the top left, and the strongest is going to be on the bottom right. More on that later on. For the second question here, we're interested in calculating the H plus and the OH minus. Remember, I can't just from reading that part say, oh, it's overall acidic or overall basic. Remember, water has this property to self-ionize. Water will always regenerate a little bit of hydroxide in an acidic solution. It's going to always regenerate a little bit of acid in a basic solution. More so, you can tell your answer, when you get a chemical like HNO3, ask yourself, what is this? Is it an acid base? Is it a salt? Is it strong or weak? So we see that this one here has an H. I would expect it as an acid. You can check your table. HNO3 is one of those top 6 on the left-hand side here. This is a strong acid. So therefore, as a strong acid, it ionizes 100%. Because I know HNO3 ionizes 100%, the math of this is going to be fairly easy. We have 16 molar of our nitric acid. Because I ionize 100%, this whole box breaks up to become 16 molar H plus, 16 molar NO3 minus. The NO3 minus is going to sit around being a spectator. I'm not worried of it. I already know that the hydronium is H2O plus is the same as H plus. I now know that it's really, really acidic, 16 molar. But although in your container, we start off with just a bunch of water, right? We toss in enough HNO3 so that it's now 16 molar HNO3. The concentration of H plus in solution has gone way up. Water will still self-ionize to a little degree. Water will still naturally reform a little base particle, but as we would expect, it's not going to be a lot. We had one nice math little connection here. Kw is equal to the H plus times OH minus. That was from the water equation. Well, I do have water in the beaker, so I can use this here. Kw is a constant I would memorize. 1 times 10 to the negative 14. The H plus, you're telling me currently is 16 molar. What should the hydroxide be? How much should the water self-ionize so that these two things multiply can give you Kw? 1e negative 14 divided by 16 gives us an X value, or a hydroxide concentration. Hydroxide is actually 6.3 times 10 to the negative 16. And again, I just want to imply to you here, just because we know the solution is very, very acidic doesn't mean we can't have base particles around. Water will guarantee it that there's always some hydroxide so that these guys here can multiply to give Kw. Right? Now, let me make the conclusion here. We know it's very acidic solution here. The H plus was a nice number. It was 16 molar. It was very big in comparison to the hydroxide, which was a really, really tiny number. Right? What we're going to do in this lesson here is we're just going to flesh out a few more calculations. Essentially, the big idea that we're introducing here is I don't like the fact I need to carry around these negative powers. Now, of course, scientific notation actually helps you out already, but is there a way to put me on a scale that actually has gotten rid of these 10 to the power negative 7, negative 9, right? I want to get rid of that. The general way we're going to do it here, I'm not going to change the H plus and hydroxide. Those are the exact amounts. But what I'm actually going to do is I'm going to introduce to you 2 rulers. One ruler we're more familiar with. That ruler is called the pH ruler. I'm going to give you the definition. pH, to get on the pH ruler here, you need to take the negative log of the H plus concentration, right? Now this one here, it wasn't a problem to begin with, right? 16 molar, that's a nice number. It didn't have a horrendous power, but let's just get ourselves on this ruler here. Let's figure out what is the negative log of 16. I know you may not have done logs in math yet, but pretty much log is a button on your calculator. You just press log, okay? There is a negative as well that sort of flips the scale around. If I take the negative log of 16, I basically sort of convert that a little bit here. My pH is actually going to be negative 1.20. So that's what being on the pH ruler actually means. I'm watching the H plus. The logarithm, as we're going to see more so on the base side, the logarithm will take care of this 10 to the negative part for me, and the negative will make sure my scale is flipped. So if you think back to the pH ruler, 7 is the dividing line. This is only true at 25 degrees. I'm going to end off with a question later on, what if we're not at 25 degrees? But 7 is the dividing line. We assume that this was neutral. I'm going to mention to you here, this is a pH ruler. pH, although we are looking at the H plus, depending on where I am on the scale, I may be acidic, I may be basic. We've already talked about here, the most acidic ones are the ones that have the least pH. So pH 6, pH 5. we usually ballpark at around 0 and 14. We're now a pH of negative 1.20. We're way over in the acidic region. So in this case here, we are very, very acidic. Very acidic actually has the lowest pH. Think of pH here as the number on the scale. The number is very, very far away from the 7, very, very extremely acidic. Basic would be the other side. Even though I'm watching H+, I could get pHs of 8, pHs of 9, so on and so forth. Those ones there would be basic. In fact, the larger the pH, the bigger that number is. If I use this just a little bit confusing terminology here, if I say the pH increases means I'm getting higher and higher up on the scale. pH increases is actually a way of saying more basic. And I'm definitely nowhere near that side of the scale this time. Okay, so that's just introducing to you this pH scale. It's trying to address these powers of 10. Again, we really didn't have much of a problem with this H+ currently. Let's try on the other side here. Because I'm going to be looking at OH minus, I don't want to carry around these powers if I don't have to. I'm actually going to do pOH. The P stands for power of OH. And pretty much anytime you see P anything, it's going to be negative log of, in this case here, OH minus. And this time here, we will actually see, well, how does this negative log bit, how does it actually get rid of the power for me? If you know in math class here, logarithm is actually the inverse of an exponent. It's not really a surprise that it brings it down. I'll show you more detail afterwards. So let's just try it out here. So I just gave you a new definition here. P anything, power of OH here, is the negative log of that number. Let's just try crunching through the math here. What is the negative log of this really, really tiny number, 6.3 times 10 to the negative 16? Again, it's just a button on your calculator if you haven't learned logs yet. Negative log of, make sure you have in brackets, 6.3e negative 16. And you notice the number coming out of this is a lot nicer, 15.20. It's representing the same number. It's still very, very low concentration OH minus, but the pOH is actually 15.20. If we actually match up on a pH scale here, it would still match up to pH of negative 1.27. I just want to show you just mathematically here why this logarithm, why does this help. Let's just do a little bit of detail, just for as a quick aside here. So I want you to think here, what happens when you take negative log of this number, 6.3 times 10 to the negative 16? Now this will take a little bit of background with logarithms here. There is a log rule that says when you log two things that are multiplied, it's like log of the first thing plus log of the second thing. It's just that I have a negative in front, so I'm going to say plus a minus here. Right. So the log rule that I used there was log a times b is equal to log a plus log b. So I see a times b, so I just separated the a and the b part out. It was just because I still had that negative, I just distributed that back in. You can try typing these two parts here separately. What's negative log of 6.3? The part that wasn't a power to begin with, no problem, negative 0.799. The part that was a power that I wanted to get rid of, what is the negative log of 10 to the power negative 16? Basically, this one here ends up being 16. Again, log is the inverse. It's the opposite operation of exponent. It basically brings the 16 back down. I don't like the fact that this is negative. That's why I put that negative there to end up being a positive here. We do end up with a nice conclusion here, though. This is where 16 minus 0.799 ended up giving 15.20. In terms of significant figures, for scientific notation, these ones here are significant. This one here is a 2-digit number. The logging, that part there, didn't actually fix anything. In fact, anytime you log it here, it's always going to end up as digits that are to the right of the decimal place. The only reason why the pH or pOH here might have numbers before the decimal place was due to this power part. This part here is definitely not significant. So therefore, the conclusion I want to take from this, even though the pOH ruler is going to be 15.20, our significant digits are only after the decimal place. Okay. So for pH, pOH, we're going to do pKW later on. The significant figures, significant digits are after the decimal point. So when I have a pOH here of 15.20, even though I still have to write 15.20, the significant parts here is just this 2 sig figs for that 20 part of it. Okay, just like when I write a scientific notation number here, the significance comes from the base number. Is it important for me to tell 10 times 10 to the negative 16? Yes, it is, because that tells you where my decimal place here actually ends up. All right. So just watch out for that here. That's a really important conclusion for sig figs here. The significant part comes after the decimal place. Okay. Now we do see that both of these scales here, pH and pOH here, they both refer to this log. That tells us that both of our rulers, these ones here, are actually on a logarithmic scale. Probably the only example you've seen for logarithmic scale so far is something called the Richter scale. Let's think an earthquake magnitude scale. We go 0 and we go up to 10. Okay, it can even go beyond that, okay, if it's a really, really bad earthquake. Even though this Richter scale here makes it look like, sorry, I don't have 10 spaces there, but even though this Richter scale here makes it look like the steps are linear, in fact, we know if I have an earthquake of magnitude 1 and an earthquake of magnitude 2, the magnitude 1 earthquake will be 10 times stronger than a 0 earthquake. The next step, which looks evenly spaced, is actually 100 times. It's in powers of 10, first thing, and it's also increasingly hard to actually get to the next step up. So sort of the same idea here with this acid-base scale here. We had calculated in a previous lesson here, 10 to the negative 7 molar is supposed to be neutral. To get to pH of 6, you actually need to become 10 times more acidic, so 10 to the negative 6 molar. But what about 10 to the negative 5 for this pH 5 here? That's actually going to be 100 times more acidic here. The reason why we ballpark it 0 and 14 is because it's increasingly hard. As I start getting like 1,000,000 times, 10 million times more acidic here, it's getting really hard to push very far past it. This one here, the reason why we're so far into the negatives, first thing, HNO3 is a strong acid. We know it's a one-way arrow, and it's also a really high concentration. Concentration will also affect where the pH, where I land on this ruler here, because the pH is going to look at the H plus concentration. Okay, so just keep in the back of your mind here, we are a logarithmic scale. Every step is 10 times harder than the one before it. They always like asking you this question, oh, a pH 5 against a pH 7, how much more acidic are we? You just count the number of full steps. One step is 10. Well, the pH 5, let me actually write this down words for you here, just like on the earthquake scale, a pH of 5 is 100 times more acidic than a pH of 7. Because acidity is measured by the H plus concentration, you can say the H plus is 100 times bigger, right, for the pH 5 than the pH 7. Even though it looks like a linear scale, it looks like a flat, nice and even scale here, it's actually not flat. Every step is 10 times harder than the one from before. Okay? So that just introduces another nice math question for us here. What I want to do here, I want you to find for me, calculate the H plus, the OH minus, the pH, and pH for a solution with pOH. Let's do 3.57. Okay. What I want to emphasize with this question here is they are asking us H plus. Doesn't suddenly mean it's acidic. They're asking us OH minus. Doesn't mean it's basic. Even asking us pH. pH is just a ruler. Wherever I land on this ruler here, I could be acidic, I could be basic. None of this tells me acidic or basic. The only part that decides it for me is when they actually give you a value. I have a pOH. On my pOH ruler, I'm at a 3.57. The question is whether I'm acidic or basic. Okay. So imagine taking your solution. You have a pOH meter, and the pOH meter just reads for you 3.57. Because this is a P something, this one here, the significant digits are actually after the decimal place. Okay. So far, all I've told you is pOH, by formula, is the negative log of OH minus. Right? So far I know 3.57 is equal to negative log of OH minus. This is going to eventually get me back to hydroxide. If I know hydroxide, I'm basically home free. Through Kw, hydroxide can get H+, and if I know H+, I can get pH. In fact, every solution can be described with H+, OH minus, pH, and pOH. Once you know one of these numbers, you know them all. I'm just going to show you the math here once. How do we undo this definition of negative log of OH minus? Two things to push back over. First is the negative. Let's make it negative 3.57. That's the logarithm of OH minus. Again, I'm assuming some of you may not have seen logs here, but log is the inverse operation for exponent. Basically, I need to take the exponent again to get rid of this log. There's a couple ways of showing it. Probably the easiest way is just to use words to say anti-log. 3.57. On your calculators, this would be shift log or second log, right? It's the second function. Pretty much here, I would take the anti-log. That's going to get rid of the log function for you. Even if you have done logs in math class here, very rarely do you do anti-log, so this might still be new. It's just anti-log is typically, I know it's an exponent, but I know we're in base 10, so sometimes the anti-log button is written 10 to the power of. So if I have 10 to the power of anything, that basically is anti-log. Essentially, that gets rid of the log for me, and this gets me back to the hydroxide concentration. If I go anti-log of negative 3.57, the calculator spits off a number 2.69 times 10 to the negative 4. Let me just keep track of sig-figs here. Remember, p anything, the significant digits are after the decimal place. This should be a 2 sig-fig number. When I have it re-expressed in scientific notation, I still want it as a 2 sig-fig number, so I still want to write this one here as 2.7 times 10 to the negative 14. Or sorry, negative 4. Okay? That actually already starts implying to me what's acidic or basic. If it's still not immediately clear, let's figure out what the H plus is. Remember, we had our Kw expression, the self-ionization of water. It gave us a nice connection between hydroxide and H plus. This time I know hydroxide, I can use the Kw expression to figure out what the H plus is. H plus multiplied by this 2.7 times 10 to the negative 4 number. The H plus concentration is therefore 1e negative 14 divided by this whole answer. 3.7 times 10 to the negative 11. If it wasn't immediately obvious to you already, well, let's take a look at the concentrations. The OH minus is a 10 to the negative 4. That's way bigger than the H plus, which is a 10 to the negative 11. So looking at the size of these numbers and from what we've done before, because I have more base than acid, right? Remember, a basic, I know it's basic. A basic solution doesn't just have to contain hydroxide. It just needs to contain more of the base particle than the acid particle, right? And at that point there, I realize, oh, a pOH that's less than 7 actually means basic. I'll draw it out for you in a second here. Lastly here, if you know the H plus, you can still find the pH. Wait, I thought the pH here was an acid scale. No, pH is just the name of the ruler. pH does do negative log of H plus. It's just where do I land on this ruler here? Well, let's take negative log of this 3.7 number times 10 to the negative 11. I already predicted that was basic. I'm predicting it's going to be something that's bigger than 7. So negative log of this answer here, lo and behold, it gives me 10.43. Now this is a p something number again, so therefore the significant digits are again after the decimal place. And there we go, we're on our ruler, we're bigger than 7, so we're definitely going to be basic. I'm going to summarize these calculations for you just to be clear here. Pretty much all 4 of these numbers that I asked you for. I asked you for H plus, I asked you for OH minus. I now, in this lesson, asked you for pH and pOH. Pretty much all 4 of these terms are connected. If you have one of them, you can get the other 3. We've already done this first conversion here. Our first conversion is through Kw. It's H plus times OH minus. If we are at 25 degrees, we can even punch in 1.0 times 10 to the negative 14. That's our constant at 25 degrees. Okay. If I want to go from H plus to pH, remember our solution was, let's put it in a log scale. The pH is actually the negative log of H plus, or the pOH, watching the OH concentration, is the negative log of OH minus. Okay, so those are 2 separate rulers. We just undid the math here. How do I go from something that's pOH, how do I get back to just the OH? I had to pull the negative over and I had to anti-log it. So in this case here, going in reverse, a little bit harder. I can say it in words. I can say, in that case there, it's anti-log negative pH. Or you can write anti-log here as that 10 to the power of. It's like 10 to the power of negative pH. Right, that's how you do in reverse. How about the connection that's missing here? Could I go from pH to pOH here? I'm going to show you a little bit more math here. Let's say we started with the Kw expression. Since the p anything here would have negative logged it, I'm going to imagine negative logging both sides. You never need to repeat this derivation for me. Negative log of the Ka, I'll color code it for you, Kw. I'm going to go negative log of the H plus times the OH minus, right? I'm going to use that log rule again. When I have log of 2 things multiplied, it's like log of the first plus log of the second. So negative log of H plus added to another negative log of OH minus It's the conclusion you need out of this, so you don't need to repeat this at any point. Well, negative log of kW is as simple as it could get. Remember we said negative log of anything is written as p of that thing. So this one here is actually going to be pKW. What is negative log H plus? Oh, that's just pH. What's negative log of pOH? Oh, it's just pOH. And surprisingly here, what's ended up happening, we've ended up making a relationship here. While it used to be a multiply, when you start taking exponents and taking logarithms, a multiply ends up becoming a plus. So this is a very general formula. The pKW is equal to pH plus pOH. That gives us a nice connection between those two terms here. If we are at 25 degrees, if you try doing negative log of 1 times 10 to the negative 14, you're actually going to get 14 equals pH and pOH, right? So therefore, if you have one of these, in this question we had pOH, we undid the pOH to get to hydroxide, we used kW to get H+, we did negative log it to get pH, but now that you have this box here, you're more than welcome to go, oh, my pOH here was a 3.57 in my question, let's go 14 minus this just to verify. 14 minus 3.57 gives us our very same 10.43 that we had from earlier. I just want to show you sort of mathematically as a diagram here what this does here. We are very familiar with the pH scale. Again, 7 is the nice dividing line. We have acids that have, let's say, from 0 to 7, that's going to be acidic. When 7 to 14, this one here is going to be basic. Because of this nice little link here, where the pH and the pOH always have to add to give 14, we can actually line up our new ruler. Our new ruler actually watches pOH. When a pH is 7, the pOH also has to be 7. 7 plus 7 is 14. In this question here, we had a pOH of 3.57. 3.57 here was actually basic. Where's basic on my pH scale? Well, basic is actually higher than it. So imagine taking this, imagine this were a meter stick, and imagine just flipping the meter stick around. So we have 7, 3.57 is down here. When I have a 3.57, 3.57 plus a pH of 10.43 adds to give 14. So you start seeing that the pH is actually just the reverse. It's like the ruler has been twisted around. So on the pOH scale here, less than 7 actually means basic. It actually corresponds to all these bigger than 7 pHs. Bigger than 7 actually means acidic. And if you just line up the rulers in this fashion, if I have a 0 pH, that's going to be a 14 pOH. If I have a 2 as a pH, and I'm going to have a 12 as a pOH here, that's how you read sort of this acid-base scale. But again, sort of the conclusion there is, if you know one of these, you can use this box here and you can navigate around to get to the other ones. All right? One last question for you. We've been emphasizing here pH of 7 here. This is our nice neutral point. But I want to emphasize to you, it's neutral only at 25 degrees. I'm going to end off this lesson here with one last calculation. I want you to find for me, explain how pure water can have a pH of 6.50. Okay? Normally when we look at that, we're going to say, well, 7 is the dividing line, less than 7 is acidic, right? This is suddenly souring on you. But again, we had alluded to this in an earlier lesson. Pure water means things are still neutral. Neutral doesn't mean we can't have acid or base. It means that the acid amount has actually matched up with the base amount here. So how is this possible? How can it be that pH 7 was supposed to be neutral, but this pH here is actually less than 7? We want to look at our water equation. Let's see the self-ionization of water. Water is in equilibrium with H plus and OH minus. This one here is an endothermic reaction. That's important. I have a pH that's a little bit less than 7. pH less than 7 would usually mean more acidic, right? So let's just start off with that. This is more acidic than we're used to. To be more acidic, that means we have more H plus. So more acidic means I have more H plus. Which way did the equilibrium shift to make more H plus? If I shift to the right, I cause water to produce H plus. That would make more H plus. If I shift to the left, I'm going to take the H plus that I have, remove it, and I'm actually going to lose H plus. Well, in our first case here, because the pH 6.50, it's more acidic than pH of 7, I actually have more H plus. I know my equilibrium has had to shift right. What do you have to do to temperature to cause it to shift right? Knowing that this is an endothermic reaction, you would have to have heated it up. All right? So How can we explain this here? First thing, I know I'm not at 25 degrees, and I can actually predict for you, am I hotter than 25 or cooler than 25? You can say we are hotter than 25 degrees. So therefore, the stress is going to be increased temperature. Which way does Lister tell you predict for us here? The shift is going to, although I heat up the entire box, I look at that heat term, the heat term goes up, it shifts to the right. So equilibrium goes towards products. Right? So far from what we said, well, the product concentration of the H plus and OH minus, the H plus concentration goes up. Oh no, more acidic. More acidic means I go lower on the pH scale, so that means pH decreases. That's more acidic. Why doesn't water suddenly sour on us when we just heat it? Well, it turns out every time I shift to the right, when you create one more H plus, you also create one more OH minus. So in this solution here, how do we keep neutral? The 6.5 pH does actually mean more acidic if our OH minus is equally more basic. If we get more acidic and more basic at exactly the same rate, if the H plus and the OH minus still equal one another, we can still remain neutral. So again, this is very strange here. We have a situation that when we shift, not only does the H plus go up, the OH minus also goes up. We also become more basic. The pOH also decreases. That becomes more basic here, such that when I go kW, kW is always supposed to be H plus times OH minus. In this case here, we have a situation where the H plus is higher, the OH minus is higher. I would expect that the kW here only depends on temperature. Great, this is a temperature shift, and therefore we can actually predict kW is actually bigger than the 1.0 times 10 to the negative 14 that we're used to. So therefore, just to sort of allude to you here, we're used to pH, the dividing line is 7. As you get more acidic, we lose base particle here. All bets are off if we're at a different temperature. If we're at a different temperature here, either in this case here I increase the temperature, I produce H plus and OH minus at the same amounts, or I decrease temperature, I make it less acidic and less basic at the same amount. My pH could be bigger than 7, although we're still neutral, we still have the H plus equal to the OH minus. Okay, so phew. Next time you actually boil water, it doesn't suddenly become acidic nor basic. It's actually becoming more acidic, more basic at exactly the same rate. So you can actually say sort of mathematically here, the pH has dropped, more acidic, but you can also say the pOH has also dropped, more basic, and they've matched up to each other. Okay, 1-to-1 ratio. Okay, so definitely practice some questions here. That finishes off a little bit of the math. We'll qualify this a little bit in upcoming lessons, and we'll be ready for the next part. Thanks, guys.